Welcome to today's Explainer. I'm honestly so thrilled you're here because we are diving into something, well, something pretty mind-blowing. We are stepping into the high-stakes, hidden world of maintaining active, mega-machinery pipelines. Just imagine the vast networks of pipes beneath our feet, carrying highly pressurized oil, gas, or water. They're literally the arteries of our modern world. And today, we're going to look at how engineers perform what is essentially industrial surgery on these active pipelines.
Picture this. You've got a massive pipeline. It's fully charged, pumping hazardous or essential stuff. And you need to cut a brand new hole right into it. Oh, and here's the kicker. You absolutely cannot turn it off. Shutting down could mean an entire city loses its gas supply, or a plant loses millions of dollars in a matter of hours. So how on earth do you safely breach that pipe without causing a disaster?
So here's our roadmap for this explainer. We'll start with the pipeline problem, figure out what hot tapping actually is, and then walk through the three main steps of the process: the split T, the valve, the machine, and finally, the final cut.
All right, let's jump right into sections 1 and 2, the pipeline problem and what exactly is hot tapping.
The ultimate workaround for this problem is a process called hot tapping. Basically, it's how you take a new branch connection from an operating pipeline without any shutdown whatsoever. It lets a live, fully charged mother pipe be tapped safely. But, this isn't like taking a hand drill to a PVC pipe in your garage. It's a highly choreographed, super intense sequence of events designed to prevent massive spills or literally explosions.
To pull off this kind of magic, engineers follow three really specific steps. First, they provide what's called a split T. Second, they install a very specific type of valve. And third, they mount the huge cutting machine and make the actual breach. Every single step requires incredible precision, and it's all about containing that intense pressure before the hole is even made.
Okay, moving on to section 3. Step 1, the split T.
So the split T, it's not some off-the-shelf part you just pick up at a supply store. It consists of a lower half and an upper half that has a branch connection and a flange, which is basically a projecting rim used to attach other parts. It's custom fabricated from super heavy steel plate. Why? Because the inner diameter of this split T has to perfectly, and I mean flawlessly, match the outer diameter of the mother pipe. It acts like this reinforced armor shell hugging the pipeline right where we want to cut.
Once they lock those two halves around the live pipe, they've got to join them permanently. The split T is securely welded on all sides. We're talking heavy-duty circumferential welding around the ends and longitudinal welding right down the sides to join the top and bottom. The split T basically fuses to become one with the running pipe, and they don't just cross their fingers and hope it holds. These joints are rigorously tested using a meticulous die penetration method. Absolutely zero microscopic weaknesses are allowed.
Which brings us to section 4, step 2, the valve. Now, choosing the isolation valve to bolt onto our split T is a massive make-or-break moment. You absolutely must use a full-bore gate valve or a full-bore ball valve. Why full bore? Because when you open it, that pathway needs to be completely clear so a giant main cutter can pass straight through to the pipe. If someone accidentally used a butterfly or globe valve, total disaster. Those have internal shafts and mechanisms that would physically block and foul the cutter, completely destroying the machine and ruining the entire operation.
Once we've got the right full-bore valve, it gets carefully hoisted up, and its flanges are securely bolted completely tight to the upper flange of our split T. Think of it like building a secure airlock. We now have our permanent branch connection and a heavy-duty gateway that opens to let the drill in and slams shut to trap the pressure later. It's locked, loaded, and perfectly aligned.
All right, section 5, step 3, the machine.
Let's talk about the machine itself, because this thing is an absolute beast. It features a central main shaft, a small pilot drill extending out the middle, and then this huge main cutter that carves out the actual hole. You swap out the cutter depending on how big a branch you need. And you're not powering this with a battery pack, right? To drive through heavy steel, it's powered by a dedicated diesel engine operating heavy-duty hydraulics. Pure, unadulterated hydraulic force slowly pushing and spinning that cutter.
Just to put this into perspective, 1,400 kilograms. That is the weight of this hot tapping machine. That's over 3,000 pounds. Because it's so incredibly massive, a crane has to carefully hoist it up and meticulously lower it to bolt directly onto the top flange of our open gate valve.
But wait, before any cutting actually happens, safety is the absolute #1 priority. The entire rig, the split T, the valve, the machine, is pneumatically tested.
First, the system is flushed from the top with nitrogen gas. This pushes out any air so there's zero chance of an explosive mixture inside. Then engineers actually go around with soap water, yep, just simple soap water, checking every single flange joint for the tiniest bubbles that might give away a leak.
And get this, they don't just test it at the normal operating pressure. They crank that nitrogen feed up to 1.1 times the design pressure. They intentionally overpressurize that empty space between the drill and the pipe to guarantee that when they finally breach the live, charged pipe, there will be exactly 0 leaks. It's a non-negotiable safety checkpoint.
And finally, Section 6, the final cut.
Here's how the actual cut goes down. The hydraulics fire up and the shaft comes down. First, that smaller pilot drill in the center makes contact and punches a tiny initial hole right through the pipe wall. Next, and this part is just genius, once the pilot drill is inside the pipe, these special catching rods or little knobs mechanically pop out from the drill bit. Third, the massive main cutter finally reaches the steel and slowly slices through the complete periphery to create the full-size branch hole.
Now pause for a second. You just carved a heavy, solid, circular chunk of steel out of a highly pressurized pipe. Where does it go? You absolutely cannot let it fall inside, right? It would be swept down the pipeline like a cannonball, completely destroying valves and pumps downstream. That cutout piece is called the coupon. And remember those catching rods that popped out earlier? Because they deployed on the inside before the main cut was finished, the pilot drill physically holds onto the coupon, trapping it so it can be safely pulled out.
So with the coupon trapped securely by the drill bit, we hit the grand finale. The hydraulic machine retracts, pulling the whole shaft, the cutter, and the coupon all the way back up through our open gate valve. The very second that drill clears the valve, boom! Operators slam that full-bore gate valve completely shut. The high pressure is instantly sealed off. The running pipeline is totally secure. Then they safely unbolt and dismantle that 1,400-kilo machine. You're left with a perfect, leak-free, permanent branch connection ready to use. And the main pipe never even stopped flowing.
So the next time you turn on your tap or fire up your gas stove and you get that perfect, uninterrupted flow of resources, maybe ask yourself, was this flow made possible because somewhere down the line, a crew performed a flawless hot tap? It's this incredible, hidden piece of industrial surgery that literally keeps our modern world running smoothly. I really hope this explainer gave you a newfound appreciation for the wild engineering behind it all. Keep learning, and I'll catch you on the next one.